Good morning, everyone. My name is Akshat Pandey. I am currently a B.Tech Computer Science and Engineering student at Manipal University, Jaipur. My registration number is 242703001. In this video, I will demonstrate 4 practical cryptography concepts using CrypTool 2. The topics covered in this demonstration are as follows. The first one is the Caesar Cipher encryption and frequency analysis attack. Second is the AES encryption and avalanche effect. Third is RSA public key encryption and decryption. And fourth and the final one is the password strength analysis using entropy. So for this demonstration, I would be using the CrypTool 2, which is a visual cryptography tool that allows us to simulate encryption and algorithms and security attacks through workflow diagrams. Now I will begin with the first task, that is the Caesar Cipher analysis. So if we see the interface of this platform or this tool, CrypTool 2, it has some predefined templates for each of the cipher and each of the cipher attacks. So if we look for the Caesar Cipher, which is somewhat like this, first, I demonstrate the Caesar Cipher, which is one of the earliest classical encryption algorithm. The Caesar Cipher is a substitution cipher, where each letter of the plaintext is shifted by a fixed number of position in the alphabet. Now, on the screen, we see the Caesar Cipher workflow. The first component is the text input component, which contains the plaintext message that we want to encrypt. Below it is another text input component that defines the alphabet, which specifies the characters used in the cipher. Next, we have the number input component, which specifies the shift key value. In this example, the key is 5, meaning every letter will be shifted 5 positions forward in the alphabet. These inputs are then passed to the Caesar component, which performs the actual encryption process. Finally, the resulting ciphertext is displayed in the text output format. As we can see, the plain text has now been transformed into the ciphertext. Here, for the demonstration purpose, I took this as the plain text. From this is the cryptography is the practice of secure, and I have mentioned my registration number and all also in this plain text. And this is the corresponding ciphertext which is generated after performing the Caesar Cipher algorithm. One thing should be noted that I have written my registration number here, and it did not get encrypted. The major reason for this thing is like it only works on alphabets. It does not accept your numbers to be get encrypted. That's one of the major drawback of this algorithm. So this is for the purpose of encryption. If I want to show the decryption of it, so I would be simply copying this text output and would be putting it as an input, as it would be like now the ciphertext to plain text conversion. And now when I run it, as you can see, I have run it and I put it this plain text and I got the corresponding ciphertext to it. So that's how the Caesar Cipher works. Now, if we see for the frequency analysis of this attack, I would be demonstrating a ciphertext-only attack using the frequency analysis, and this is the demonstration. This is the very same, what you could say, the very same ciphertext which I have provided it for the purpose of the demonstration of attack. In this workflow, the text input component contains only the ciphertext, meaning the attacker does not know the original plaintext on the key. The ciphertext is sent to the frequency test component, which calculates how frequent each letter appears in the ciphertext and displays it as a bar chart. These frequencies are analyzed by the Caesar Cipher helper component, which compares them with the known frequency distribution of the English language. Since the cipher only shifts letter but does not change the statistical distribution, this pattern remains visible. Using this information, CrypTool correctly determines the shift key, which in this case is 5. The Caesar description component then reverses the shift and recovers the original plaintext. The decryption message appears in the text output component and detected key is displayed in the key output component. So that's all about the analysis based on the frequency test. Now if we see for the brute force, like the brute force attack, now I demonstrate another ciphertext only attack, which is called the brute force analysis. The Caesar Cipher has only 25 possible keys, since letter can only be shifted between 1 to 25 positions. In this workflow, the counter component iterates through all possible shift values. For each key, the Caesar component generates a candidate plaintext, as you can see here. These are the like list of all possible plaintext for the particular ciphertext. The dictionary component checks whether the resulting text contains recognizable English words. The correct plaintext contains meaningful words, so the system identifies it at the mostly likely solution. So here's the mostly likely solution, which has been separated from the all possible plaintext, and it has been demonstrated or decrypted. This demonstrates that the Caesar Cipher is insecure because the key space is very small and can be easily tested using the brute force. So as we could conclude that the Caesar Cipher is highly vulnerable. Now if I go for the second task, that was the AES cipher working. For this, let me first explain you what is AES. AES stands for Advanced Encryption Standard, which is a modern symmetric encryption algorithm widely used for the secure communication. In this diagram, the text input component contains the plain text message, which includes my registration number. The message is here 2427, my registration number, and registration number of Akshat. Next, the data entered in the AES component which performs encryption using the AES algorithm with a 128-bit key in the CBC mode. The encrypted binary data is then converted into hexadecimal format using the string encoder component. Finally, the encrypted ciphertext is displayed in the text output component. Now you could see I got the hexadecimal result in the ciphertext. Now I want to demonstrate the very important effect which is observed in the AES, that is the avalanche effect. The avalanche effect means that a very small change in the input produces a large change in the output. Initially, my input contains my registration number ending with 11. Now I change only one digit, making it to end with 12. That is like I just did this much. And when I play it, like when I execute it, you can see the significant difference and the changing in the ciphertext. Like just a minute. See, it was this thing and now it became this. After running, we can see it. Even though only a single character was modified, the output is entirely different. This property ensures that the attackers cannot detect pattern between the plaintext and ciphertext, making AES highly secure and reliable option for the encryption and decryption process. I would be moving on the third task, that is RSA encryption. I would be showing both things, the encryption and decryption as well. So, unlike the symmetric encryption, RSA uses two keys, a public key for encryption and a private key for decryption. RSA encryption workflow is somewhat like this. On the screen, we see the RSA key generator component, which generates the key pair using large prime numbers. Next, the text input component contains all the plain text. Like the plain text I have provided here is this: my registration number, certify this work. The plain text is converted into binary format using the string decoder component, which is here. The binary data is then processed by the RSA encryption component, which encrypts the message using the public key. The encrypted result is then converted into a hexadecimal format using the string encoder component and display the text output component. This is our ciphertext generated from this corresponding plain text. So now if we talk about the RSA decryption, here the ciphertext, let me first open the window on this thing. Here the ciphertext is first converted from a hexadecimal into the binary using the string decoder component. The data is then passed into the RSA decryption component, which uses the private key to recover the original plain text. The decryption message is displayed in the text output component, and this demonstration demonstrate how RSA uses a two separate key, enabling the secure communication even over insecure networks. Now I would be moving to my final part, that is the password checking using the base of entropy. Entropy measures the randomness and unpredictability of a password, usually expressed in bits of security. See, if we talk about for a weak example password, like I change the password to just my registration number, that is 2427030011, and when I execute it, I get a score of 23, which is a weak password and with an entropy of 2.446. It is highly vulnerable for the attacks. So the factors that changes that highly affect the security of password is the password length, character diversity, and presence of symbol and number. The tool calculates the score, bit strength, and entropy value and estimate how long it would take for a brute force attack to break the password. Since this password contains only numbers, it is classified as weak and it can be cracked quickly using the brute force attack. So if I want to convert it into a strong password candidate, I would simply add some characters and alphabet. That is 2427, my registration number, @Akshat. So as you can see, the entropy just rise to the 3.455 value with a score of 100 and a complexity of very strong password with bit strength of 85. Because the number of possible combination becomes extremely large, the time required for a brute force attack increases drastically. This demonstrates why strong passwords should include multiple characters, types, and sufficient length. So if we talk about the conclusion of this whole demonstration of 4 things, the following things could be dropped as a conclusion for each one. The first is the weakness of the Caesar cipher due to the frequency analysis and the brute force attack. Second is the avalanche effect in the AES encryption. Third is RSA public key encryption and decryption. And fourth and the final one is the password security using entropy analysis. These examples show how cryptographic systems protect information and why modern encryption algorithms and strong password are essential for the ciphertext. Thank you for your patience listening and have a wonderful day ahead.